everything came into creation in the gap between fire and ice. The world tree, Yggdrasil, connects the 9 worlds, including Asgard, home of the Aesir, the Norse gods, and Helheim, or simply Hell, the underworld, where the dead go. And there is Valhalla, the hall of the honored dead, a majestic, enormous hall ruled over by Odin himself. Those who die in battle, if judged worthy, are carried to Valhalla by the Valkyries. In Valhalla, these warriors join those who have died in combat, the Einherjar, and legendary heroes and kings in preparation to aid Odin during Ragnarok, the twilight of the gods. In Ragnarok, Odin will fight the wolf Fenrir, and Thor will fight the serpent Jormungand. Jormungand surrounds Midgard, the middle realm where humans live. And Thor will fight valiantly, and Thor will win. He will kill the serpent, but the serpent's poison will kill Thor in the end as well. The 9 worlds and Yggdrasil. Asgard, home of the Aesir. Midgard, home of humans. Helheim, home of Hell and the dishonorable dead. And many more worlds. The Vanir, the Light Elves, the Giants. But aside from my obvious interest in the subject, why are we talking about the Norse? Well, today our goal is to examine some useful tools for analyzing and fixing problems in your program. We are going to learn about Valgrind and Helgrind, and it would do you well to pronounce them correctly. The endings are pronounced grind and not grind. Where do they take their names from? Valgrind is the gateway to Valhalla, a gate that only the worthy may pass. Helgrind is the gateway to Hell. So, is your program worthy? These are analysis tools for your C and C++ programs. They can be applied to other things as well. And they are terrible for performance, but they're wonderful for finding errors in your program. And so, to use them, we will start the tool of our choice and tell it what program we want to run and observe. The target program runs under the supervision of the tool that we've chosen, and then this does result in running dramatically slower than normal, but we get checks and monitoring of the program, and we can get some useful information out of that if debugging symbols in our compile are enabled, particularly if you want stack trace to be useful. Now, this lecture is unlike the others that we have seen so far, as though that were not obvious, in that it mostly involves actual demonstration as opposed to content in the notes or the slides. Now, given that this is a video, doesn't really make much difference to you, I don't think. But if, of course, this were being held in a lecture hall, this would be one that you would not want to miss as a result of the fact that the demos just wouldn't happen again. Now, we will not have time for absolutely everything that is interesting about how to use Valgrind and how to use Helgrind, so you'll have to play around with it yourself. Fortunately, there is an exercise for this, which gives you some experience with it. And truly, you should be an expert in it, or at least competent in it, when this course is done, because from here on out, we will expect you to use it on your programs. We will. We will check. Did you leak memory? Do you have concurrency problems? Now that you know, you got to use it. Be brave. Be valiant. See you on the field of battle at Ragnarok. Now, these are really analysis tools for your programs, and I'll give you a little introduction to the theory before we go on to some of the examples. The Valgrind tool suite definitely slows down performance by a lot, like 100 times.
but they are excellent at finding errors in your program, which ultimately is the goal. And to run it, you start the tool of your choice, and you give it some direction saying this is the program I want you to run and supervise, and it will do so and produce a report at the end that tells you what it finds, if anything. You have to remember to enable debugging symbols, otherwise you don't necessarily get useful data out of it. Your stack traces might not be that helpful. We'll start with Valgrind's default tool, Memcheck. And if you don't specify using another tool, it runs Memcheck. And the goal of Memcheck is to look into memory reads, writes, to also intercept calls to allocate and deallocate memory, and check that they are valid, see that they are okay, and make sure everything is correct. And at the end, you will find out, is your program worthy? Can it pass the gate? Can it enter into Valhalla? Okay, so Memcheck, was originally intended for something like a C or C++ program, but that becomes obvious when we look over the kinds of problems that it can find. Here's a brief overview. Number 1, accessing uninitialized memory. Number 2, reading off the end of an array. Number 3, memory leaks, that is, failure to deallocate memory that has been allocated. Incorrect freeing of memory, you free it twice or something like that. This will be detected, although freeing memory twice in your program frequently causes a crash, so that's easy to spot right away. Incorrect use of C standard functions like memcopy. That's one of those things where it is possible to get it wrong, and it's easy enough for Valgrind to detect it because it can see the call to the C standard library. Use after free. If you try to use memory after it has been deallocated, again, normally that doesn't crash your program immediately sometimes, and you'll only find out really when it's a problem that it does crash or there's a vulnerability that is uncovered as a result of that. And also asking for an invalid number of bytes in the allocation, which can happen if you malloc some user input times the size of the array or something, and the user gives you 0 because they're trolling you. You could ask for an invalid number of bytes, and you could actually end up with a problem as a result of that. Or a negative number could also happen if you have like an integer overflow or something. That would not be good either. So you will get that reported by Valgrind. Now you might be thinking, wait a minute, what's the point of this? All of this is impossible, as Thanos would say. Or I suppose if you wanted a Clone Wars type meme, at least I think it's Clone Wars, I could have put Anakin here saying, I don't have such weaknesses. But there are actually ways that you can end up with memory leaks in Rust. And some of the examples are, number 1, explicitly calling the leak and forget functions. You can, in fact, choose to do this on purpose. There are a couple of corner cases where you'd want to do this. Forget, in particular, is good for cases where something is being handed over to another language. You're writing this module in Rust, and it hands some memory over to a C program, or a C module of your program, and it's the job of the recipient of that memory to deallocate it when it's done. You can tell Rust, forget about this, not our problem anymore. If the C part, however, forgets to deallocate it, then you end up with a memory leak. So forget is not necessarily the recommended way to do very many things, but there are valid use cases for it, and if something goes wrong, we end up with a memory leak. Obviously, unsafe code allows us to break a lot of the rules some of the rules anyway, that we're used to in Rust that would ensure that things don't get forgotten, that we don't read an uninitialized value, or that we don't access something we're not supposed to access. And same thing with calling functions in other languages. Again, if there's some C interop that you've got going on, the C code could still do it wrong. In which case you end up with reading off the end of an array or something because that part's in the C code and it doesn't check that the array index is valid. And you can also have a leak based on reference count cycles where you have just a loop of things where reference count 1 points to reference count 2, points to reference count 3, points back to 1, and you end up with a cycle, meaning that memory is never deallocated. That one is not, in the strictest sense, a memory leak, in the sense that the memory that you're talking about still has valid references to it, but it's unreachable and it's not useful, and there's kind of no benefit to keeping it around, so you don't want that, and Valgrind will help you find it if you need. The goal, when we get to the end, is to see something that looks like this. All heap blocks were freed, no leaks were possible. This isn't always going to be the case. For some reasons or another, there are potentially some things that are not our fault that we can't do very much about. You should also be sure to take the suggestion to use the leak check equals full option, which gives you some more kinds of error, but also some more details about what went wrong. In the example below, which is admittedly a C program, just to show you an example of finding a memory leak, the lines 49 and 24 are the locations of memory allocation that lacks a matching deallocation. A tool like Valgrind is unable to tell you how exactly to fix the problem. It just tells you, here's where the memory was allocated. You have to figure out what is the lifetime of it so that it can be deallocated when you're finished with it. Obviously, Rust's compiler tries very hard to figure out the lifetime of things, so it knows to deallocate stuff when the owner goes out of scope, and that works a lot of the time. But if you're doing anything with unsafe code or interop with a different language, you may not have that guarantee, in which case the Rust language doesn't know how to deallocate it, and you have to figure out when to drop it. Again, Valgrind won't tell you exactly where that drop or free or what have you should go. Again, particularly if you have a C interop here where you pass some memory that you allocated in Rust into your C code. It just says, here's where it came from. You figure out how long it should live. Anyway, when we take a look at the output, there are a few different categories of things. First category is definitely lost. This is a memory leak. Fix it. There's really nothing else to say about that. This is what happens when you allocate memory somehow and don't deallocate it. That's a memory leak. Fix it. Easy. Indirectly lost is usually a problem with a pointer-based structure. So you have a linked list, and you have leaked the head of the linked list, and all the remainder of the items in the list are still there. Usually fixing anything that's definitely lost should be enough to clear up things that are in the indirectly lost category. Just means you didn't clean up your structure correctly. Possibly lost. Valgrind isn't sure. The program might be leaking memory unless you're doing some weird pointer arithmetic type stuff where you're pointing them to the middle of an allocated block as a way of iterating over something, which you kind of shouldn't do. Again, Rust discourages you from doing this, and you would only really do it in unsafe code, but if you did, it could be reported as possibly lost. Still reachable. This is memory that was allocated and might otherwise have been freed, and it got to the end of the program and it hasn't been deallocated. You could, so it's not lost, so it's not obviously an error, but still reachable usually means that you're missing a deallocation of some sort that should be there just for the sake of always following the rule that says if you allocate memory, you should deallocate it. And finally, there is suppressed. You can choose, if you wish, to configure the tool to ignore certain things. If you know that this is not a problem and it's a false positive, you can put something in the suppression list, which will then just have its count appear under suppressed, but not actually be reported as an error. We're not going to configure the suppression list or anything in the examples that we're going to do, but just for a more advanced use case, you could. On that subject, it's important to know what to ignore and or what is out of your hands. Sometimes this happens in a C program, especially where you find that you get an error reported on something like pthread create because it says some memory was allocated in pthread create and wasn't deallocated somehow. And there isn't very much you can do about that. It is a bug in a library that is not under your control. This could happen really with any library. And if that's the case, you have to analyze it and say, is this something I can fix or is it not? If it's not, don't feel bad. There's I mean, you could probably report it as a bug to the maintainers of that library, or if you're feeling really ambitious, submit a patch. And sometimes actually somebody's already done that, and it's just you need a newer version of the library to get that change. But you have to think carefully by looking at a given stack trace. Is this in my code? Is this something I can do something about? If it is, then fix it. If it's not, then don't get upset about it. Don't think, oh no, this is going to be a problem. I'm going to lose all the marks on the assignment as a result of this. That's not how it works. It's important to know what's within your control and what is not. As before, we're going to demo this using the ECE servers. This is especially important because, at least at the time of recording, Valgrind just doesn't work under Mac OS for whatever reason or reasons. The information about the kernel necessary to make this work hasn't been released, and therefore Valgrind just reports when you try to install it with Homebrew that it won't work under the modern version of Mac OS, and that's all she wrote. So we'll do it here on ECE servers as per usual. We'll take a look at the source of the program that we're going to run. This one is nothing special. It is just creating a bunch of threads, and that's what we'll do. So let's set up leak check full, and then we can't use the cargo run thing because then we'll try to profile cargo as opposed to the actual target that we are interested in. But this one is easy enough to find. The compiled version is under target/debug/thread, and we'll see. And interesting. So we end up with some reachable blocks, and if I actually ask show leak kinds equals all, it will tell us some more about what it found. Okay, what happened here? Well, 32 bytes in one block are still reachable. And ultimately, if we look at it, here's a big hint about what's wrong. Unsafe external C function, blah, 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 which is used to create pthreads with attributes. So this is a good example of the kind of problem that actually we can't really do anything about. You'll notice here there aren't clear pointers to any lines of code that we actually wrote. We have our main function, which spawns a thread, blah, 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 which uses the Unix threads, all that stuff. I don't think this is anything we can do anything about, and it's one of those where we have to learn to recognize what's within our control and what is not. Let's take a look at a program that has what is effectively a deliberate sabotage in it. If we look at this code here, the important thing here is on line 11, where I added an explicit call to forget a particular piece of memory, and we're going to do that several times. You could pretend, of course, that we're actually giving it over to some other code, but if we call forget, let's see what happens. Another, incidentally, possible use for forget is it takes ownership and gets rid of something without running its destructor. If for some reason you need to not run the destructor, it is a way to make that happen. I don't know off the cuff any scenario where that would make sense, but you could if you need. Interesting. Okay. What do we see? Okay. Why didn't any memory leak? Any ideas? Yeah, because the thing that we created on the stack there is it's just a simple type. Let v equals 42. It's an I32. So yeah, we actually needed to be heap allocated for there to be a memory leak. Otherwise, it just gets trashed at the end of that loop iteration. So let's try again, shall we? Move occurs. Oh, because it's going to change on every iteration of the loop, we could... Yep, we create it once and it's moved, so we just put that inside the loop instead. That's better. And we'll ask Valgrind to take a look now. All right, so we have definitely lost behavior now. 36 bytes in 9 blocks. Makes sense. Okay, we have the still reachable thing that was mentioned earlier, but what actually happens here, 36 bytes in 9 blocks are definitely lost in this loss record because we do a malloc here. And it happens, in our code, we did something wrong. I mean, I intentionally did something wrong, but it tells you actually relatively little about what actually occurred, which is a little bit unfortunate. Makes uncovering an error, if you have one, a little bit harder. But the important things to note are really here, that there's a closure inside of main. That's where I've actually allocated that memory. And the allocation takes place as an allocation of a box of I32. Eventually, of course, that goes down into the system memory allocator and eventually ends up being a malloc. Fine, that's okay. But it's a little harder to read than we would have seen for the equivalent C program, where it would say, all right, here's exactly the line and here's exactly what happens. Even though this does tell you the line, it's less obvious because it's a closure, so there's no function name associated with it. If I move that content to a function, it would make it a little bit easier to see. As we've discussed, though, fortunately, this kind of memory leak is much less likely to happen in Rust as compared to in other languages, so the fact that narrowing down exactly where the problem occurs is a little harder here should not make your life too much more difficult.